your email. All right. So I will take account that you can. All right.
Welcome everybody. Thank you for coming. It's a real pleasure for me to introduce Marcelino. Marcelino is a researcher in the National Research Council here in Madrid. He studied in the University of Valladolid chemistry. I did study everything before coming. He made his PhD in astrophysics in this university, in the Autónoma University. Then he went to several observatories for his postdoc. And he came back to Spain with a Ramón y Cajal fellowship, and now is a researcher in the National Research Council, as I said before. His field of expertise is molecular astrophysics, and this is what he's going to be talking about today. So I hope that you all enjoy. I say before him that some of these slides will be in Spanish, some in English, because it wasn't clear the language that he had to use. So it's just apologies for that, but thank you.
Thank you, Cristina. Well, hello, good morning, everybody. So, as Cristina said, I'm working on molecular astrophysics. Basically, this is the study of molecules in space, okay? As she said, I have some slides in Spanish or in English, so it's a kind of mixture, but I will speak in English during the talk. I hope that that's okay. Okay, so I have prepared a little bit of introduction to the subject because I can imagine that you have different areas of expertise here. And then I will show you some particular cases, scientific cases in which our group has been working in the last years, okay? So to show you a little bit what kind of work we do. Oh, sorry, this is...
Is a reminder that you have to do so.
Luego te llamo, ¿vale? Que estemos... Sorry. Okay, sorry for that. Okay, so I'm going to work to speak about molecules in space, okay? With this work, with the arrow, or this one, okay. This one, no? Yeah, on the space, okay. Okay, so the first part is about tell you a little bit about molecules in space, okay? Some basic concepts. So basically, the story started like 100 years ago, in the 1920s or something like that. So at that period, basically there were telescopes that operated in the optical part of the electromagnetic spectrum on ground, and they were typically observing stars or nebula. Okay, so they observed the spectra of these stars, and they observed some absorption bands and absorption lines in the spectra. Okay, and these lines could have three origins. Okay, the first one could be originated in the surface of the star itself. So this will be lines of photospheric origin. Okay. Some other lines of absorption could have been produced in the own atmosphere of our planet. So it will be the telluric lines. And there will be another type of lines that will be produced by some media in between the star and us. Okay, so basically by interstellar clouds. So then of this type of lines, interstellar lines, there were several that were not known. I mean, the origin, the carrier of the lines were not known. So some people started to postulate that perhaps molecules could be the carriers of these lines. Okay. At that time, that was the first three molecules that were suggested to be present were rather simple. So the radical CH, CH plus, and CN. Okay. At that time, this hypothesis was not very well welcome because people tend to think that in the interstellar medium the conditions are very harsh, very hostile for molecules to survive, because there you have a lot of energetic radiation, ultraviolet radiation. So people didn't think that molecules could survive in the ISM, in the interstellar medium. Okay. But then that occurred in the early years of the last century. And then things changed a lot just after the Second World War, when the radio astronomy started to be developed. Okay, so this allowed to open a new window to observe the universe. So basically, here you have the opacity of the atmosphere, of our own atmosphere, as a function of the wavelength. You have here the optical region of the electromagnetic spectrum. You can see that here the atmosphere is completely opaque. You cannot observe from ground. Here in the infrared, you have some specific windows, but this is quite opaque also due to water vapor. And here you have this window that is the radio window, which is completely transparent, so that allows you to observe the universe and get through to the atmosphere. Okay, so after the Second World War, the radio telescopes start to be developed, and this allowed to make new discoveries. So basically, they discovered several key points in astronomy. They discovered the one line of atomic hydrogen, which occurs at 21 centimeters. And this allows to observe atomic hydrogen everywhere in the universe. They discovered some phenomena they call quasars, which in fact are active galactic nuclei, so galaxies that emit very powerful radiation. They discovered also the pulsars, which now we think they are neutron stars that rotate very rapidly. They discovered also the cosmic microwave background, which was like the first empirical proof of the Big Bang theory. And then, for interest to us, they discovered also a lot of molecules in space. They started to discover a lot of molecules in space. The first ones were rather simple. They discovered the hydroxyl radical, ammonia, water, formaldehyde, carbon monoxide, etc. To have here one of these observations, you can see some. This is a spectrum. So you can see here the observations at these points, and this was the theoretical prediction of one ammonia line. Okay, so that was the status of the things in these years. So right now we know that there are we have discovered more than 300 molecules in space. We have here some slide showing the molecules by number of atoms. Well, there are a lot, so I will just say that looking at the type of molecules we are detecting, most of them are, a great fraction of them are organic, so they contain carbon. This is curious because carbon, even if there is an abundant element in the universe, is, for example, less abundant than oxygen, but there are much more molecules containing carbon than containing oxygen, and this has to do to the chemical properties of carbon that we know here in Earth, that is very versatile to form bonds. So that happens also in space. Okay. We start to discover, I mean, there are some kind of typical molecules, simple molecules, but we start to discover molecules with a certain degree of chemical complexity. For example, this one, which is called glycolonitrile, which has two functional groups, in one nitrile, one OH. So we start to discover molecules with several functional groups, which start to have some interest in biotic chemistry. Okay, and also some molecules which are quite curious, very large molecules. This is the fullerene, as you probably know, the C60 that was discovered. This is one in the optical. So we start to discover molecules with increasing chemical complexity, and this is also happening in the very recent years, that we are starting to unveil the chemical complexity in space. Okay, and just to show you with this slide the role of Spain in this, I show you the cumulative number of molecules discovered in space as a function of the time by a telescope that has made the discovery. Okay. So you can see here several telescopes that are in the US, Japan, and also there are these two that are here in Spain. One is in Guadalajara, in Jeves, close to your place. Another one, and this is the one, the Jeves 40 meters because it has a diameter of 40 meters. There is one, the Iran 30 meters, that is in Hueleta, in Granada. And these two, and this plot is from a couple of years ago. So I didn't update. Now I think the Jeves has surpassed the Iran 30 meter. But you see that these two telescopes are really the leaders in discovering molecules in space, and they are located here in space. Okay. Which is something that when I was in the university, I listened to some talk that they were saying that Spain is quite powerful in astronomy. That I was very surprised with that because I didn't thought Spain was powerful. But in some areas we are really leaders. Okay. So, okay, we know about molecules, but where are molecules in space? When we look in with our eyes to the sky, we see basically the stars. So the light from the plasma that is in the stars. So one may think that what this is a question that a child made some days ago. That what do you have in the dark, like in between the stars? So typically, I mean, we do around with our eyes, we cannot really see, but what we have, some of the dark places are in fact interstellar clouds. It is if you, instead of looking with your eyes, you look into with CO. Let's say you have a kind of glasses in which you are sensitive to the molecule carbon monoxide. This is a map done in the radio domain of the spectrum, and you see all this. This is the Milky Way, basically. You see all the molecular clouds that are present in our galaxy. So basically, we don't see the molecular clouds in the visible, but when you look in radio, you start to see all these molecular clouds arising. And all these clouds that are interstellar clouds are basically essentially composed of molecules. Okay. Molecular hydrogen is the most abundant one. The second one is CO. That's why this is used to trace the molecular gas. And then we have all these other molecules you have seen in the previous plot. Okay. And what is why is interesting to observe these molecules or to study these molecules? You have here what we call the cycle of matter in our galaxy. Okay. We know, and this is a major achievement of the last century, that we have been able to locate the different regions we observe in space into this evolutionary cycle. We know that the different objects that we observe are in a certain evolutionary cycle. Either they are evolving to form a star, or they are evolving from a star that is dying, but they are immersed in this cycle. We know that the stars, at some point at the end of their life, they will either explode as a supernova or eject most of its mass to the interstellar medium. Okay, and this will be a material process because nucleosynthetic reactions have been taken inside. So this enriched material will go to the interstellar medium. At the first stage, they will form quite diffuse clouds, so relatively with very low densities, very exposed to UV radiation. By gravity, these clouds will start to collapse. You will have at some point dense clouds, and inside these dense clouds, we know that the stars are formed. Okay, at some point, after a star is formed, they will start to accrete material around, forming disks, are called protoplanetary disks. And we know that in these disks is where planets form at some point. Okay. So the interesting point is that molecules are present in all these stages. So studying molecules, we can study the transformations that take place from when a star is dying and when the star is forming and when planets are forming. So we can study the formation of planets, the formation of stars, and the death of stars. Okay. So just to show you that really molecules are present in each of these stages, here this is some maps and real maps of a red giant, which is a star that has evolved and is about to die, let's say. And we see here, this is the red giant will be somehow here, and this is the material that has ejected outside the red giant. And we see if we look in the visible, we see all this light scattered in dust. And here, this is if we look in a molecule that is CN, we see this very nice ring, which in fact is not a ring, but is because this is a map in velocities. We in fact is tracing a spherical hollow shell. Okay. What other regions? Diffuse clouds. Also, there are molecules. I already told you that these clouds are exposed to UV radiation. So the chemical complexity you have here is not so large, because at some point UV radiation destroys the molecules, but still you have simple molecules like hydrides, you have water, CH. So these are the regions where the first three molecules were discovered, CH, CH plus, and CN. So some molecules survive here, even if you have intense UV radiation, okay? And then when we move evolution to a later evolutionary stage, dense clouds. Dense clouds are very curious because when you look then in the visible, you basically see dark. These are these dark regions. You see stars everywhere and some dark regions. These are in fact called dark clouds because when you look in the visible, and they are dark because they contain molecules and dust. And the dust is absorbing the visible radiation from the stars behind. Okay. So when you see in the visible, you see dark, but when you look in CO, you see in fact bright. All the molecules are inside these molecular clouds. Okay, and this is the regions where at some point stars will form. So by studying the molecules, we can study how the stars are formed. Okay, and in fact, if you look if you want to study these regions in the visible, they are very opaque, and you cannot get in what's going on inside. By studying molecules, you can get you can go inside the clouds. Okay. And also these other regions, if we want to understand how planets are formed, which is a hot topic right now in astrophysics, you can also use molecules, okay? Because you have, basically these protoplanetary disks are made of dust and molecules, and gaseous molecules, okay? So you can observe either the dust. This is a real image obtained with the ALMA observatory that is in Chile. It's an assembly of many radio telescopes operating as an interferometer. And they were able that now we are starting to see this kind of disks with these gaps that we think are due to the formation of planets. Okay, that here some material has disappeared because it has gone to form a planet. So now we can really study in situ how planets are being formed. And you can also study the gaseous counterpart, okay? It's some molecules, and this is telling you how is the distribution of the different molecules, and where are the ices and the snow lines located in this system, which is very relevant to the overall formation of planets. The process of formation of planets is very different if you have most of the material on ices or if it is in the gas. And in the internal regions, you have that temperatures are high, so normally you don't have ices, but from a given distance, you start to have all the material on ices, and this accelerates the formation of the planets, okay? So people are very interested in trying to observationally locate these snow lines, so the regions where ices start to appear, because this is very relevant to the formation of planets, okay? And we have also, of course, molecules in the atmospheres of planets. We know that in our solar system, you have here the spectrum of Earth, Venus, and of Mars. You have here this strong absorption due to CO2, which is responsible for the global warming here on Earth. And also, not only in our solar system, but in other in other systems, in other planetary systems, we have started to characterize the chemical composition of the atmosphere. This is the first molecule, the first observation of a molecule in a planetary atmosphere outside the solar system. These photometric points were used to say that water vapor was observed in this planetary atmosphere. Okay, at that time, this was very controversial, but right now it has been confirmed with much better observations. And in fact, right now with the James Webb Space Telescope, we can do infinitely much better and get really fine detailed spectra with a lot of features due to molecules coming from the atmosphere. So we can start to characterize the chemical composition of the atmospheres of planets outside the solar system. Okay, and this is very interesting. People is very interested in trying to locate or to identify some kind of molecules that could indicate presence of life and stuff like that. Okay, this is also a very hot topic right now. So I will now switch a little bit to talk more on more chemical aspects of astrophysics, so more astrochemistry. So basically, being very simple, we have a kind of dichotomy between equilibrium and kinetics, talking about chemistry in space, okay? So the high density environments, normally, also if the temperature is high, will tend to have the chemical composition close to thermodynamic equilibrium or thermochemical equilibrium, okay? This happens not very often in space, but it happens in the stars, these brown dwarfs and the atmospheres of planets, okay? Normally in these environments, a good approximation is to consider that the chemical composition is given by thermochemical equilibrium, but these are the only few environments where we can make this assumption. And in this case, to compute the chemical composition is relatively easy because you just have to minimize the Gibbs energy, and at some point you get the chemical composition, okay? You just need thermodynamic properties like enthalpies or entropies, okay? Relatively straightforward. The thing changes when you have a low density environment. In this low density environment, the chemical equilibrium assumption is no longer valid, and you have to go to chemical kinetics. So you are very out from chemical equilibrium. Why? Typically, these interstellar clouds have been talking to you. You have diffuse clouds or condensed clouds. The densities here are very low. You have a few particles per cubic centimeter. In these diffuse clouds, you have the order of hundreds of particles per cubic centimeter. In the dense clouds, you have more. We call these dense because they are denser than these ones, but still they are super low densities, of the order of 10 to the 4 particles per cubic centimeter. Just to compare with the density in this room, here we have of the order of 10 to the 19 particles per cubic centimeter. So you can see that even this density cannot be reached in the best vacuum laboratories, okay? So, and this makes that this low density makes that collisions are happen very rarely. I mean, I think that the calculation said that every some weeks, one molecule meets another one, collides with another one. Most of the time they are isolated. And this makes that that chemistry is slow. But the good point is that this the time scales here are so large, these clouds live for millions of years, and still, even if the collisions are very rare and happen not very often, still they can chemical reactions can work, okay? So just to give you an example of how far from chemical equilibrium it is the chemical composition of the interstellar clouds, you consider this very simple chemical system, okay? You have on one side CO, a molecular hydrogen that can be converted into methane, and water. You compute the equilibrium constant for this system, and you compute it at very low temperature, at 10 Kelvin, you will see that the equilibrium constant is 10 to the 1,000, something like that. So this is telling you that at very low temperature, this chemical system is completely displaced and shifted to the formation of methane and water. While observationally, we know that the two molecules more abundant in the universe are CO and molecular hydrogen, okay? So if chemical equilibrium works, we should not have CO at all, and it is the most abundant molecule after molecular hydrogen. And this is because chemical kinetics is regulating and governing the chemical composition of clouds, and not chemical equilibrium. So we can see that at the end, interstellar chemistry is a kind of search for the global minimum in the energy of the system, but there are so many barriers that you never reach this global minimum of energy, okay? You are always settling that local minimum. A kind of example. And how we do to compute the chemical composition in this equation? Then we have to go to chemical kinetics. We have to rely on rate coefficients of chemical reactions. We have to plug them into these rate equations and build a chemical model, and this will tell us at some point what is the chemical composition, okay? And the point is that these chemical models normally have in order to properly describe the chemical compositions, you need to include like thousands of reactions, and not all of them, of course, have been very well studied. So there are important uncertainties associated to this way of computing or calculating the chemical composition. So just to illustrate you a little bit, molecular astrophysics is a quite interdisciplinary field because it involves, like I have summarized in like 3 aspects. Okay, on the one side we have the astronomical observations that you can make with radio telescopes or with infrared telescope or even optical telescopes on ground, on space. And you get from this, you can get maps of the brightness, you can get spectra, and these are the observations. This is normally what motivates the new discoveries. But then to interpret this astronomical data, in this case, a spectrum, you need to build models because otherwise you cannot say much about this. You can just say that this line belongs to, I don't know, CO or whatever other molecule. And just, you want to say more and interpretability that you need to build a model. First thing you need to do is to build a model, what we call a radiative transfer model. You need to describe how the photons are being propagated inside a cloud and what are the photons that are escaping and will eventually reach your telescope. You need to build a kind of synthetic spectrum based on parameters, on a model, and then compare with the observation. And this starts to allow you to tell something about the physics and chemistry of your object. Okay. And then if you want even more and you want to understand how a given molecule is formed, what are the chemical processes behind the formation and destruction of molecules, you need to go to these chemical models, in which you introduce the rate equations I showed you before, and at the end you get some predictions for the abundance of the different molecules. Okay, in this case you get the abundance as a function of time, and then you can compare and you can try to see if you understand how the molecule you have been detected, you understand how it is formed, or you don't understand, and then you have to come back to your chemical model to see what's going on. Okay, so this is basically the 3 pillars of molecular astrophysics, and the point is that these models rely on many parameters that for many species are not known. Basically, you need calculations, ability calculations, you need experiments to provide many physicochemical properties of molecules. You need to provide the spectroscopy of the molecules, of course, otherwise you cannot detect them. You need to provide cross-sections of collisions and of reactions. You need also to understand and to provide many processes that happen in the surface of the dust grains. Okay. At the end, this makes that molecular astrophysics are a very interdisciplinary field, and in fact now they have started to talk about laboratory astrophysics, and this involves both calculations and experiments that are specifically designed to understand some given astronomical problem. Okay. So that was a little bit of the intro. Now I will tell you a little bit what some real cases that we do in our department. Okay. The first one I think illustrates relatively well this multidisciplinary aspect of molecular astrophysics. It's a case of spectroscopy in space. Okay. So the story, which is a real story. We were observing this molecular cloud with a telescope in Granada. At some point, we observed a series of lines that we didn't know which molecule was causing them. Okay, so a priori they were unidentified lines. We started to think what could be the molecule behind these lines. But doing a little bit of basic molecular spectroscopy, we made some hypotheses, okay, that this could be the transition, the 1 to 0 rotational transition of a molecule. And if that hypothesis is true, then our molecule should have, like 2 heavy atoms. By heavy, I mean nitrogen, carbon, or oxygen, and may or not have hydrogens. Why? Because from the position, the 72 gigahertz, we can get the rotational constant, and we can get the moment of inertia of the molecule. We can have an idea on what are the weight, what is the weight of our molecule. So this constrains a little bit which kind of molecules could be candidates for that. So to test that hypothesis, if this is really the 1 to 0 line, a transition, then there will be a 2 to 1. The next transition should happen at twice this frequency. Okay, and this frequency was available, so we sent a proposal and look at. And in fact, we saw also a forest of unidentified lines here. And with a further test, we went for the next transition, the 3 to 2, and we also observed some lines that were not identified. So now, with that, we were pretty sure that we have a new molecule. We have these transitions that belong to that molecule. Now, the point was, which is the molecule, okay? Of course, there was no laboratory data. So there were several spectroscopic arguments to guess, okay? Basically, our molecule has to have this composition, 2 heavy atoms and some or not hydrogens. Our molecule, because what we see is not a single line but many lines, it has to have some fine and hyperfine structure. So this makes that our molecule cannot be a closed electronic cell molecule. It has to be a radical, cation or anion, because it has to have some fine structure, which only happens for radicals. Also, because the splitting of the lines was so large, it cannot, this cannot be explained only with the fine structure. We have to go for the hyperfine structure. So this makes that some nitrogen or hydrogen must be present in order to cause this hyperfine structure. Okay. So what we did, Carlos, in fact, was doing calculations to compute the rotational constant of many potential candidates. You can see here the ones that we explored. At the end, we arrived at the carrier was H2NC, which was quite exotic. We didn't expect that. The match between the astronomical spectroscopic constants. I mean, we were able, with the lines we observed in space, to provide a fit to all these spectroscopic constants. And the comparison with the calculations were pretty good. And we were pretty sure that we identified this molecule. But we were not expecting that, because in fact this molecule is a high energy isomer. H2NC has a more stable isomer, which is H2CN, which was in fact known to be present in interstellar space. And in fact there are other isomers here, HCNH, with the hydrogens in the 2 sides. And the difference in energy was quite high. 30 kilocalories mole is quite high. And in spite of that, we were observing that the abundance of this guy and of this guy was similar. So the abundance ranking was 1, even if the energy difference was so large. So this is, again, stressing that the chemical composition of interstellar clouds is very far from chemical equilibrium, okay? But still, we wanted to understand how this guy is formed. So we observed also. We sent another proposal for the telescope. We observed more clouds, and we found the molecule in many other clouds. And we noticed one kind of correlation. I mean, the abundance of this new molecule, H2NC, correlated with the abundance of ammonia, which is here. Okay, so you can see that as the abundance of ammonia increases, you can see that the abundance of H2NC increases. And this is telling us our idea was that ammonia could be a precursor to form this guy, and the more abundant ammonia is, the more abundant the other guy is. And to test that, we thought about the reaction between atomic carbon and ammonia. Okay, it happened that this reaction was measured in the laboratory. It was found that it is very rapid at a low temperature. However, some calculations predicted that H2CN should be the major product and not H2NC. Okay, but we were relatively sure that, or at least our astronomical observations suggested that the different proofs, also the correlation with ammonia, suggested that H2NC should also be formed in this reaction. So I just went to see Fabio from Fero, who's in our department, And he studied again this reaction between atomic carbon and ammonia. And it happened that the relative contribution or the relative production of these two guys depends very heavily, is very sensitive, the difference in energy between these two transition states, okay? And this difference in energy is so small that it's on the order of the error of the calculation. So we are in a case in which we are very sensitive to something that is the order of the error of the calculation. But at the end, she tried several methods and predicted what should be the abundance ratio from that reaction between these two isomers, and he got that. Depending on the method, you can get that this ratio is below 1 or close to 1, while the observation was telling us that the ratio is of the order of 1. So if he found that with some methodology, this ratio could be close to 1, okay? But again, perhaps we will be never sure unless some experiments are done, because the difference in energy between these two transition states is so small that it's on the order of the error of the calculations. Okay, but I like it to show that because I consider it's a nice example of how a given astronomical case can start to you can start to pose more questions and start to involve some colleagues doing different stuff. Okay. So some other second topic I would like to talk to you. It's about these guys. So red giants. So stars that are about to die, let's say. So these stars are very, very curious from a chemical point of view. First, they are giant because of their name. And giant means that the radius has increased by many orders of magnitude. Typically, the radius of the order of a few astronomical units. So the radius of our sun, when the sun will become a red giant, will be located somewhere here. So you see here the Earth. Okay. Okay, this is like 5,000 million years still we have. But this will be the destination of the sun if we understand well physics, what's going on. Okay, these giants, because they expand so much, the surface temperature decreases a lot from the 6,000 Kelvin that our sun has in the surface. These guys, the temperature decreases to 2,000, 3,000. Okay, so they become red. That is because the name red giant. So they are giant and they are cool, so they are red. Okay, and in these objects also there is a process that is very curious that happens inside. So because if they grow so much, convective processes can be happening inside, and this makes that you can selectively bring out to the surface some carbon. And if you bring enough carbon, you can make that here at the surface the gas become carbon rich, because normally oxygen is like twice more abundant than carbon. So most of the universe is oxygen rich, but in these objects you can become carbon rich if you are able to bring enough carbon so that the carbon to oxygen ratio becomes higher than 1. Okay, and this makes a lot of difference for the chemistry. Okay, so we have red giants that are oxygen rich and some others that are carbon rich, and the chemistry is completely different. Why? Because of the molecule of carbon monoxide. Okay, you make a calculation and you predict what is the chemical compositions for the typical conditions of the surface of these stars. You will conclude that carbon monoxide is a very abundant molecule, must be a very abundant molecule. At the typical conditions of typically 1 millibar and 2,000 Kelvin, carbon monoxide is predicted to be one of the most abundant. So in the case in which you have more oxygen than carbon, you will lock all the carbon into CO, you will have the remaining oxygen to form oxygen-rich molecules. So in oxygen-rich stars, you will have water, OH, and oxygenated molecules, but little or non-carbon-rich molecules, because most of the carbon is in CO. Okay? While if you have a carbon-rich situation, again, most of the oxygen will go to CO, and you have the excess carbon to form carbon-rich molecules. You will have ACN, CS, etc. Okay. So the type of molecules you observe in these two environments are very different, and this depends heavily on this ratio. Okay, and this has interesting consequences. This is just confirmation of what I told you before. Basically, you made a chemical equilibrium calculation. You see that the composition is completely different in one case and in another. In both cases, you have CO here. So, here in the oxygen-rich case, you have the water and OH. Well, here you have acetylene, ACN, etc. Okay. The chemical composition is very different. So let me introduce you one remarkable object in the sky. We call with this happy name IRC plus 10216. Comes from astronomy, infrared catalog, blah blah blah. And is in fact is the brightest objects in the sky at 10 micron, and in the infrared is the brightest objects of the sky outside the solar system, apart from Venus and in the moon only. You can see here, and basically this is IRC plus 10216 in the infrared, and this is the moon. You will see basically in this short video how IRC hides behind the moon. Okay, but the point is that the bright, you notice, is similar of the moon of this guy. So this is and why this is a red giant. It's a carbon-rich red giant that is relatively close to us. So it's on the order of 100 parsec. So it's around 300 light years. This is relatively close in astronomy for us, and it's super bright, and it has a very interesting chemistry. This is the guy I showed you before. It should be here, but we don't see really the star. We just see all the matter that the star has expelled to the outside. Okay, this is light scattered on dust, and you see the cells here. That is the matter that the star is expelling. So what do we think about the structure of these circumstellar envelopes around these red giants? We think that this is the scheme we think is happening. Right? We have very large gradients of density and of temperature. You have at the surface like 3,000 Kelvin, and in the outer layers you have tens of Kelvins. So you have a super high, super steep gradient in the temperature, super steep also in the density. You have densities here of around 10 to the 15, and then you go to a few particles per cubic centimeter. Okay. So here, this is the hot and dense. So here we have a chemical composition close to chemical equilibrium. But then it happens that this gas is being ejected. So at some point, chemical reactions are no longer rapid, and then the chemical composition gets frozen. So nothing happens from the chemical point of view until when you enter in the outer parts, UV photons start to photodissociate the molecules. It creates radicals, and these radicals again take part in chemical reactions. So we have like a given chemistry here, regulated by chemical equilibrium, and here by photochemistry or chemical kinetics. And the type of molecules we observe in both places are very different. These are maps. This is a map. We observe here a molecule which is sodium chloride, the common salt, in the gas phase. So this is a molecule, not a solid. And we observe that the brightness distribution is concentrated around the star. This is telling us that it's coming from the inner regions. But there are other molecules, like this one. This is a radical C4H, so 4 carbon atoms, 1 hydrogen, and you see this kind of ring. A map in velocity, a kind of cut in the plane of the scale. But really, you have like a hollow spherical cell, okay? And this is telling us that close to the star you have nothing, you have no this radical. At some point, when you go out, it appears, it is formed, and then gets destroyed again, okay? So this kind of maps allows us to follow really the chemistry that is going on in these objects, okay? So these are the typical molecules we are observing, all the list, around 100 in this object. Many of them are carbon-rich in this column, a few only oxygen-rich, and most of them are carbon-rich, contain carbon, let's say, okay? So I will focus on this because it was a surprise. It was discovered when I was starting the PhD. It was, in fact, the first topic I was given for the PhD to explain why water vapor was present in this object, because it was not expected at all. So it came with the satellite Herschel that was operating in the 2010 around that, and this telescope observed water vapor in this carbon-rich object. So we didn't understand what was the origin of that because chemical models didn't predict at all water. So this is the level of discrepancy, let's say. So these were like the predictions from chemical equilibrium. You have an abundance relative to hydrogen of around 10 to the minus 16, and the observations were around 10 to the minus 6. Okay, you have many orders of magnitude of difference. And we still don't understand this after 2003 or 2004. We still do not understand. I mean, we are still trying to understand. There have been several scenarios proposed. All they involve non-equilibrium processes, but we are not sure about which one is a good one. Okay, but this is still, we are still trying to understand this 20 years later. I will tell you a little bit about the carbon-rich molecules. This is very interesting because it allows you to really follow what's the chemistry, what's going on with the chemistry. By doing these maps come from ALMA, from this radio interferometer. So basically, the interferometer makes that your pixel size is very small, so you can make very precise maps like these ones. So basically here, we made maps of several carbon chains, several carbon-rich molecules, and all of them were observed as a ring, so as a whole spherical cell. Okay. Our idea was that this is a very nice case where you can really follow the chemistry almost in situ. Because we know that the gas is being moving outside, so basically the radial position is equivalent to a time. Here we will have our time 0, and then our clock starts to move, and each time corresponds to a given radius. So basically, we can follow as a function of time how chemistry happens. This is the only, I think, kind of environment where you can do this without this level of precise. Normally, your object is in a given evolutionary status, and you cannot know because the changes in astronomy involves many very long times you cannot follow in your life. But here you can follow really, because of this happy coincidence, we can follow really what's going on with time. So this allows you to make a chemical model. Okay, this is the observation as a function of the radius of the intensity of several molecules. So you can build a chemical model like this one. Basically, you follow what's going on with time. As I told you, each time corresponds to a given radius. You follow, in this case, that acetylene is injected, then is photodissociated, and C2H, the radical is formed, and this allows to form other radicals, and the same with HCN. Okay? So we build a chemical model trying to describe this, and then we compare with the observations, because we have this kind of very precise maps. So this was the calculated brightness distribution as a function of radius coming from the chemical model. And these were the observed ones. At the end, we got a good match. And at the end, what we were interested in is to understand what are the chemical processes behind the formation of this. So basically, the chemical scheme that was in the chemical model was this. So basically, from all this, we understand how these molecules are being formed. And basically, the scheme is the following. We have the photodissociation of acetylene or HCN. You have the formation of these radicals. These radicals, C2H, start to take part in some chemical reactions and form molecules of increasing length. And this is a kind of polymerization that happens in space. Okay, but here, because we have pretty good values for the rate coefficients of all these processes, we are pretty sure that we have a pretty good model of what's going on. Okay, so the combination of measurements in the laboratory of the rate coefficient, the astronomical observation, and all that allowed us to know how these carbon chains grow. Yes. Last thing I will tell about this red giants is these are also the only objects in space up to a few years ago where you have molecules containing metals in the chemical sense, okay? You have molecules containing magnesium, aluminum, sodium, and iron. In the rest of interstellar clouds, because they are cold, most of metals should be in the dust grains, forming some solids, but they are not in the gas phase. So you cannot know what is the metal chemistry going on. Okay, but here, because the temperatures are high, you can form some molecules containing metals in the gas phase. They survive, and you can characterize them. Okay, so this allows you to really test what's going on with this metal chemistry, this kind of environments. Okay, and what we think. Again, a chemical model. So these are the abundance predicted as a function of radius for all this family of magnesium molecules, very exotic by terrestrial standards, let's say. And what we think is going on here, but is still not completely solved, we think that is going on is this. That magnesium, in this case magnesium, cation is reacting with these carbon chains, forming this complex through a reaction that is called a radiative association. So basically, these two guys associate, they emit some radiation to stabilize the complex, and once this complex is formed, because it is positive in charge, it will react with an electron. This is called a dissociative recombination process. Basically, when a cation reacts with an electron, it fragments in neutral fragments. And we think that from this kind of complexes, from the reaction with electrons, all these neutral fragments that we observe are being formed. Here, Octavio, in fact, made some calculation for this process. The complicated one is this one, to know exactly what is the product distribution in this fragmentation, which is very difficult to calculate and also very difficult to measure in the lab. But we think that this is the chemical scheme that is behind all these rich magnesium molecules in this place. Okay. And I think I will tell you about the last one, the last case, which is one that we have been working on in the last 2-3 years. Okay, and it has come also as a surprise. It has to do with the large molecules in the space. If you remember this plot, here in this corner, you have some molecules which are really large. They are full elements, so the C60, 70, the cation of the C60, and also of the family of the polycyclic aromatic hydrocarbons. So several aromatic rings fused that you have here. Okay. These ones have been discovered in the last years, okay? So, but the story dates back to around 100 years ago, okay? This is optical spectrum, and as I told you, in the early years of astronomy, most things were done in the optical. And when you point to some star, I told you that there were some lines that were caused by the interstellar medium in between the star and us, and many of these lines still are not known, which is the carrier of the lines, still now. So this is one of the most oldest problems in astronomy. All these lines that are observed when you point your telescope to a given star are absorption lines that happen at specific wavelengths. And still, we don't know which are the carriers, except for 2 lines that were assigned. I will show you that. That happens to arise from C60 plus. Okay, so these 2 lines, these are called the diffuse interstellar band. Diffuse because they are observing diffuse clouds. Interstellar because they are interstellar. And they are bands but they are lines. Okay, so 2 lines were assigned to C60 plus, but still there are hundreds of lines that remain to be assigned, and we think that these arise from large molecules containing carbon. Why? Because you observe them in diffuse clouds. As I told you, in diffuse clouds you have some strength of UV photons, so the molecules have to have a certain size in order to be stable against photodissociation. The small molecules normally will photodissociate. The very large molecules, very large, are able to absorb the UV photons and then internally convert this energy via vibrations into infrared energy. Okay. But still, all of these lines remain to be assigned. So this is one of the clues that there are really big molecules in the interstellar medium. The other comes from the infrared. In the 70s, this kind of, when infrared astronomy started to develop, they started to see that these emission bands happening in the infrared, we observed almost everywhere. They coincide, the wavelengths, they coincide with the vibrations of carbon-carbon bonds and carbon-hydrogen bonds that are present in aromatic molecules. Okay, so people tend to think that these are due to polycyclic aromatic hydrocarbons, but still there is debate. There are people in the community that think that they are mostly coming from aliphatic or mixtures of aliphatic aromatic. There is still debate on this, and why? Because up to now, no individual pH could be identified. So here with these bands, because they are really broad, you are not specific. You don't know which specific pH is responsible of that. You can only assign this to a kind of carbon-carbon stretch in a sp2 hybridization, for example, but you don't know which molecule is behind that. So this makes that there is still debate until a few years ago that we started to identify unequivocally these pHs. The first one was this called indene. It consists of a ring of 6 members fused to a ring of 5 members. Okay, this was observed with a Jebes radio telescope. Up here, individual lines. These are rotational transitions of these guys, which have a very small but not zero dipole moment, so it allows you to observe the rotational spectrum. And this was the first pH that was unequivocally detected in space. The funny thing is that it was detected in a dark cloud, which is not the typical environment where these unidentified infrared bands are observed. Okay, so but at least we have the first clue that these pHs are there. Just to give you an idea, this spectra took around 500 hours of integration of the telescope. So the telescope pointing and integrating during 500 hours. Right now, I think we have data for 1,500 hours. So this is a continuum line survey to observe weaker and weaker lines. The more time you integrate, the noise level becomes lower, and then the weak features you can detect. Okay. Okay. Right now, because we have been involved in that, and also there is an American group involved in that, this is the family of pure pHs that are unequivocally detected in space, and they are the simplest one. This is cyclopentadiene, which in fact is not aromatic, but is an important cycle. We have benzene. It's not detected, but we detect the derivative with a cyano group with a CN, which is polar. We don't detect this because this is non-polar, and if you are not polar, you don't have dipole moment, you don't have rotational spectrum. Okay, related polar stuff. The same for this one. We detect, they have detected the CN derivatives. For indene, because it has a small dipole moment, we could detect it directly. And last year, we detected this one, and the American people detected. Okay, so we start to unveil this family of pHs now in space. Now the question that we can make is, how are these guys formed in space? What we don't know. Look here to this is like the abundance. This column is the abundance of different hydrocarbons in one astronomical object as a function of the number of carbon atoms. So basically the idea, and here I have plotted in blue the linear ones, and in pink the cyclic ones. So basically what you see is that if you move to increase the number of carbon atoms, you start to become more cyclic. Okay, it's just observational points. Okay, and this reminds me, this what happens to pure. We have on this side chains, and on that side cycles. Okay, it reminds me what happens to pure carbon clusters, which when you increase in size the number of carbon atoms, let's see these guys tend to be more stable in linear form, but when you increase above a given size, around 8, I think, 8, 9 number of carbon atoms, the most stable structure tend to be cyclic. So at some point, it seems that when you increase in size, the number of atoms, the more stable stuff is the cyclic ones, okay? But still, as I told you, chemical kinetics must be behind the formation of the gas, not the stability or thermodynamics. And we don't know yet how these cycles are being formed. This is a proposed scheme in which basically what we think or we are trying to test is that a bottom-up scenario, that these cycles are being formed from smaller hydrocarbons, okay? One possible scheme would be that this butadiene, that through the reaction with CH or C2H will form our cyclopentadiene or Vincent directly, okay? This is based on neutral reactions, was proposed by Ralph Kaiser, and this is a proposed scheme. And now you see that this butadiene is the key precursor of this. And then we are very interested in knowing whether butadiene is there or not. The problem is that butadiene has no dipole moment. But we can search for the cyano derivative as we did with the others, okay? So the Americans came with the detection of one cyano derivative of butadiene last year, but then we look at that at our data, independent data, and we don't see it. So we think, I mean, this is we are about to publish this. So we think that this guy, if it is present, it has a very low abundance. So we think basically that this scheme, even if these reactions are fast and produce these products, we think that this scheme is not happening in the interstellar clouds. So we have to investigate alternative schemes, okay? Right now we have Maria Mayo, who has started the PhD in our group to investigate ion neutral reactions that could be responsible for forming these PAHs, okay? Under the supervision of Herman and myself. And just to finish, tell you that we are interested in all these very large molecules that happen in different regions of in this evolutionary cycle, because at some point also, when we are interested in that to understand the picture, but also we know that at some point all this material will come to planets, to early planets. This is the material that came to the early Earth, came in the form of comets, of asteroids. Of course, we could investigate that directly on a comet, but as you may know, this asteroid does not fall on Earth because the probability has decreased now to 0.1 from this morning. So if it comes, fatal, but we can study the asteroid. But I prefer not to study that way. Okay, that's all. Thank you very much for your attention.
I have a very general question, and then I might have some others they will talk on French. I have very when you show the two telescopes that now are leading, is there any? So you said more that you don't know, but is there any reason why? Is it because the position in space? Is it because the others are not being maintained or done anything extra?
Why?
Any idea?
No, in principle, the position for the radio telescopes is not very critical because you don't need like super clear skies or clean skies. I mean, for these telescopes, they operate in regions of the spectrum where the atmosphere is relatively transparent. So you are not worried about putting it in like in Chile or in Hawaii or in the Canary Islands even. Okay, so that's not the point. The point is that perhaps it's historical. I mean, there are the story of radio astronomy started in the US, then Japan at some point joined, and later on Europe came because this telescope in Granada comes from Germany, France, and Spain, so it's participated. So at some point, right now, the telescope in Granada is one of the best ones in the world because the Europe community has a lot of interest in radio astronomy. In the US, they have also a lot of interest on infrared or other stuff, also radioastronomical community. Being large is not so important as in Europe. In Europe, the radioastronomical or the molecular astrophysics community is very important. Yeah. So that may be the reason why, and also the people behind the telescopes also makes the. Yeah.
famous because they develop cryogenic detectors.
Yeah.
And they are very specialized on that.
Yeah.
And indeed they are exporting these kind of detectors all around the world.
Yeah.
They are famous
Yeah.
for that.
Mm-hmm.
I think they have some of the best detectors for the
Yeah. The technological developments in JEVES in the last years are really impressive. In some sense, it's much better than ALMA, which is an international huge collaboration. So on that side, we have to be proud to do that. Yes.
Thank you very much for the presentation. I was wondering if you could comment a little bit on the mental experiments done in the lab for science actions and so on. What sort of method?
For the reactions you are speaking, we have experiments. Yeah, we have experiments on molecular spectroscopy just to measure the rotational spectrum, but there are others. We collaborate with people in Ciudad Real that they have a chamber where they a low density, very low, the high vacuum chamber, or at least high vacuum chamber, where they inject some stable species. They produce in situ some unstable, some radical, and they follow how they react along a given supersonic expansion. Okay, so they are measuring there the rate coefficient of the reactions, and the good point is that they can measure that at super low temperatures, around 10 Kelvin, because of the expansion. So this kind of experiments, and there are also, I mean, in the community of molecular astrophysics, there are many types. There are many people interested on ICES, so they follow. I mean, ICES opens you an own universe because the kind of processes that can happen on ICES are enormous.
And then I had another question. You talked about fullerenes. So I was wondering, are there possible other sort of carbon nanotubes like nanotubes or?
Yes, because there is a kind of we're not sure of that. We think that there is a kind of transition between the simple molecules that we can isolate and study individually and the dust grains that are composed of millions of atoms. And in between, we are starting to now study these fullerenes or these pHs, in fact, but we think that at some point there will be some transition. So at some point, there are kind of materials like the one you said that people propose to be responsible for the specific properties of the emission of the dust grains. So I mean, the dust grains, we have a lot of uncertainties on because you are not the spectroscopy is not so specific. I mean, you know more or less the chemical composition, whether it is a silicate or it is carbonaceous, but we don't arrive to the level of detail for the gas phase. But yes, that would be difficult to test. But there are many people interested, and the debate is wide concerning the gas grains and all these materials.